you have to identify some features. These features get matched automatically. The more redundancy you have, the more geometry you have around these features, the better this matching and this orientation recovery is going to be. If you have more points, even if it's not from the structure that you want, it's better. So two things really dictate the accuracy of how well these. So what ends up happening is these features, you extract the features, then it gets matched. Then those matching is used to do a relative orientation between each and every one of these stations, right? Where you've taken the picture. That relative orientation is dictated by two things. One is the redundancy. That means how many of these you have, because only 5 of these would be sufficient to recover the orientation parameters. But really, the more you have, it's just going to be a better redundancy. So you have some noise. That noise is going to get canceled out because that random measurement error is going to be reduced. That's one side of it. The other side of it is the geometry between these points. And I'm actually going to explain this as well, because I did some experiments a few years ago exactly about this geometry. If you have a coverage of the whole scene with your features, instead of having a coverage of a very small amount of it. And that actually impacts the accuracy quite a bit, it turns out. So the matching of the features, then you're going to recover this, and then you're going to be completing a dense 3D reconstruction based on that. And then you have to do some scale definition, and in this case, I did some automatic ways with circular targets, but there are various different ways that you can do it. You can even do it with QR codes if you know more or less whereabouts it's going to be. Okay, so we have essentially a set of similar points between 1 or 2 or multiple different images, and this typically is carried out through a process what we call scale invariant feature transform. We get the K matrix, which is the calibration parameters, and your essential matrix. We get the projective matrices, and this here there's a K missing. Okay, so don't freak out when you rewatch it. Then based on these, we get the relative orientation between the 2 cameras, and then from that, we basically have to go and triangulate it. And once we triangulate it, we get the final X result in coordinates. Okay, so if we have additional views, what would happen? Well, obviously, we would have to have all of these points related to that. Once we have that, then basically we perform the same for the rest of them as well, and we find the points that correspond between all 3 or more of these images. Once we have that, then we can update our interior orientation parameters, which is our K matrix, or our radial lens distortion, and then as well as our exterior orientation parameters. And we put it all in the bundle adjustment and then add the other one. That's why in Colmap, you basically get 1 by 1, right? When you do the 3D reconstruction, you do 1 by 1, you add different images to it. Okay, sparse 3D reconstruction. What happens here? You basically get a sparse 3D reconstructed based on your initially matched features. Now we have many more pixels associated with it, right? So because we have many more pixels associated with it, we need to do some sort of dense 3D reconstruction in order to be able to solve that for a full point cloud, which is basically what you get at the end of it, which is going to be after the undistortion. And the matching that you have, we basically get for every 2, we do that stereo pairing, which is going to be the pixel to pixel matching, and then we get the dense 3D reconstruction. So if your column is, let's say, 0.9 meters, that 0.9 meters needs to be reflected here. So, for instance, a Cloud Compare or any other software that imports that, you need to be able to go and identify the dimensions of this particular, let's say, column. And then from those dimensions, you would be able to identify to be multiplied by some number in order for it to basically make that 90 centimeter, right? And then also last year we talked about if we want to make it more accurate, we would have to get the 2 planes and then the other plane as well, and then get those intersections in order to identify that properly. Otherwise, we're basically thinking of it as a point to point, and those points might not perfectly aligned, might not be good. It might be a point that has more error and all of these types of things, right? So we need some sort of measure of that. And then once you do that, then you can go and remeasure it and identify that this is going to be 90 centimeters. So there's some process behind how you're going to be doing that, right? So one way that basically I used was to use these types of targets. And this is where those red dots that you mentioned, Frederick, would actually come to work, is actually for scale definition, not necessarily for matching, because you wouldn't have enough opportunities there. You would get these for scale definition. So what that means is that you get the distances that you have between them, and then from that you can know, if as long as you know the distance and you can know the correspondences, you would be able to define the scale, which is really just the variance. And for this, you get the ellipse detection. You have to match these ellipses together between images. You have to correct it for the eccentricity so that the actual center of that is measured. You need to know the actual centers in reality relative to each other. And then once you do that, basically you have to divide the covariance or the variance of one of them divided by the other in terms of the sums of them, square root of that, and that's what, or the standard deviation of the real world divided by the basically image or the object space that you get in the after the dense 3D reconstruction, and that would give you the scale. How many of these required? Well, it turns out that there's a science behind it, right? And that's why it's important to actually go and get your hands dirty with these, because, for instance, I observed that if we have good convergent images between them that go from one area to another, and by convergent, that means around a degree of, let's say, at least 80 degrees to 90 degrees. Once you have that, if you get around 5 images, you actually are not going to be getting significantly better results in terms of scale definition if you increase the number of them. So you're still getting the same images. So it's going from one corner to another corner, right? But you're not dividing it into the more points. You just 5 of these would be more than sufficient as long as they basically have that convergence that we talked about. And for this, if you do it just with the center of the ellipses, you would get it up to 1 millimeter in terms of the estimation of the radius of cylinders. But if you do it with the adjusted center, which is adjusting for eccentricity, you can actually get it sub-millimeter accuracy.